In this video, we're going to continue our exploration of the data collection plan. And in particular, we'll be taking a look at sampling and sample size considerations. And this video isn't really intended to be a deep dive in sampling and sample size calculations. I've got some links to those more advanced concepts on the course materials website. In this video, the specific learning objectives will be to take a look at why sampling is an important part of the data collection plan and some of the traps that teams sometimes slip into when they don't consider sampling. We'll take a look at two common types of data when you're dealing with process improvement project work, and those two data types are continuous data types and discrete data types. We'll compare and contrast them and provide some examples of each. We'll then provide some sample size rules of thumb for when you're collecting continuous versus discrete data. And then at the end, we'll take a look at ways to modify the measurement operational definitions that you've got for specific CTQs so that you could capture continuous versus discrete data. So before we dive into some of the rules of thumb for sample size considerations, I thought I'd answer this bigger, broader question of, why sample and why not just analyze population data sets? When we're talking about sampling, a sample is a small subset of the overall population of data that's available to you or that the organization has collected. I like to think of population data as the big soup pot. A sample is a ladle that you dip into the soup pot. The sample is supposed to reflect the population, but a sample is not the population. And so here are a couple of images that I think kind of help describe differences between sample and population. And here's the number one reason why we don't always analyze population data. Our team doesn't have the time and resources to go out and capture and analyze big population data sets. And in many poorly performing processes, that population data just isn't available. Capturing a sample is our next best thing. But even if you do have population data, I will frequently suggest that we grab samples rather than work with the whole population. If the population data set is over a long period of time and the process has changed, well, a lot of that historical data really is not a reflection of what's going on in current state. And that's the goal of your process improvement team, is not just to go out and get data and analyze it, it's to use that data to help you understand what's going on in current state. And if you've got many historical records that are not a reflection of the way the process is currently performing, it's not very useful. Samples might be a better reflection of what's going on in current state. So with that said, there are going to be cases where it's easy to access population data. Population data is a true reflection of current state. And if that's the case, you may elect to have your teams take a look at whole population data sets. Do not avoid collecting your quant data just because you're afraid that a sample might not be big enough or robust enough. Some quant data is better than no quant data. It's our job to try to make sure that we increase the knowledge level of our team and we have a reflection of what's really going on in current state. And we use this quant data to help focus in on some of the most important areas that we'll be doing root cause analysis on in the analyze phase. Samples are frequently a way that we're going to go. So before we give the sample size rules of thumb, one of the first things that you're going to want to consider in terms of how much is enough, how big of a sample size do you want, is whether or not the process data that you're collecting is normally distributed. We've got follow-up videos on ways to test data sets to determine if they are normally distributed, and it's a whole big chapter in our data analysis program. But in essence, if it looks like a bell-shaped curve, if you were to histogram out a single category type of data and it looked at like a mounded hump, you probably have got normally distributed data. And here's the thing about why normally distributed data is important for process analysis. Many process activities should be normally distributed. There is this theorem called the central limit theorem that says if you've got many underlying variables that affect your output performance that you're measuring, there are many underlying critical to quality variables that affect your output performance. With that qualification, there is a strong likelihood that you're going to have output performance that looks like a mounded hump, that looks like a bell-shaped curve, that is normally distributed. Where I'm going with this is a lot of your business data that you're collecting and analyzing in a process improvement project should be normally distributed. The central limit theorem says it should be normally distributed. Now, there are exceptions to this, and that's part of the reason why we've got whole chapters in our data analysis program on how to test if it's normally distributed or not. But if your data is normally distributed, we can start to use these rules of thumb that are coming up next. Another big consideration, though, before you ask how much is enough, is there are two big category types of data that we're often working with when we're dealing with process analysis and process improvement project work. It's continuous and discrete data types. Sometimes continuous data is called variables data, while sometimes discrete data is called attributes data. We'll be calling it continuous and discrete. Here's the difference between the two. Continuous data is measurement data where you have a nominal target and you're measuring the distance from that nominal target. Examples of continuous data could be things like physical phenomena, distance that's being measured, or temperature, or barometric pressure, humidity levels. But there are also continuous data measures that are less physical. Time-based metrics are continuous data. Monetary measures, like variance from budget, are examples of a continuous data type. If you can perform arithmetic operations and calculating averages makes sense, that's a strong indication that you've got continuous data. Discrete data types are category types of data. The best example of discrete data are pass-fail, yes, no, in-out type data. But other category types, like blood types or Likert scale values on a scale of 1 to 5 or on a scale of 1 to 3, on a scale of 1 to 7. Those are all examples of discrete data types. Discrete data is any type of data that you can count and put into different categories. Frequently, when teams think about data that they might want to collect that reflects a critical to quality variable affecting process performance, discrete is the type that is first thought of. It's a simpler type of measure. Like did the supplier provide the materials to you on time or not? Was it a pass-fail consideration? Was the form filled out completely and correctly, yes or no, pass or fail? Did the completed part pass its quality inspection? On or off, yes, no, pass, fail, in, out. These are all examples of discrete data. Continuous data, like I said before, is measurement data, time, money, weight, any of the physical phenomena, temperature, barometric pressure, or values that are averages over a particular time period, like the average performance value for a particular day over the span of multiple days or weeks. Measurement data, data that you can perform arithmetic operations on. Frequently, it's very straightforward to convert discrete data into a continuous measure. You could say, let's count the number of times the supplier provided materials on time or not. That would be discrete, pass, fail, in, out, yes, no. But we could easily convert that into saying, how early or how late did the supplier provide those raw materials and make it a time-based metric of, plus 2 days, They were 1 day early, 23 days late. That's now a continuous measure, and before, when we were just saying was it on time or not, pass fail, that was a discrete measure. I bring this up because in a moment, when we take a look at the rules of thumb, there are going to be some great advantages to continuous data in terms of our sample size rules. So knowing that you could convert a critical to quality variable from discrete into continuous by just changing a little bit on the operational definition, the measurement opdef that you craft, could be a powerful technique to help with your teams. All right, let's finally give you the rules of thumb. All right, here are our rules of thumb if we're dealing with normally distributed data, and if we're dealing with continuous data, we're looking for 30 or more data points. More is always better, but 30 is a nice kind of minimum rule of thumb for continuous. If we can capture 30 or more data points, we can be 95% confident that what we're observing is a real reflection of what's going on in current state, or if nothing changes in future state, we can be 95% confident that the phenomena that we're observing will continue to happen in the same manner that the 30 or more data points showed us up to now. Discrete data's rule of thumb, 1,400 or more data points. More is always better. If we can capture more, great. But with 1,400 or more data points, we can be 95% confident that we have an understanding of what's going on in current state or what's needed in future state. If we get less of each of these rules of thumb, say we can only capture 25 or 26 continuous records, or we can only get 1,200 or 1,300 discrete data points. It doesn't mean that we'll want to throw that data set out. It just means that we can't be quite as confident in our ability to state that we know what's going on in current state or that the same phenomena will continue in future state. Our confidence level goes down. What this does tell me, though, is that 1,400 data points is in many cases too many data points for teams to consider if they're thinking about direct observation. In other videos, we took a look at different data source locations, and if you're required to observe a phenomena and only record discrete values, that could be an awful lot of observations that you'd have to perform manually by yourself or even by your team. On the other hand, 30 or more data points, that's pretty darn easy or very straightforward to collect typically by teams, and it opens up the possibility to not only historical data in the database or survey data, but also direct observation. Notice that in both of these, there was no stipulation about the underlying population size. The assumption we have is that the population is much, much bigger than whatever our sample is. And if you have a much, much bigger population data set and your data is normally distributed, it doesn't matter that you capture a certain percentage of the underlying population. I didn't say 30 or more data points and 20% of the data set. It doesn't matter what the underlying population is as long as the underlying population is much larger. These are great rules of thumb. They help our teams in not slipping into analysis paralysis. In many cases, what I'll tell team members is if we've never captured data on performance before, it may just require us to capture 30 days, the average performance over each day. Those are our 30 or more data points that we're looking for. We're looking for a month's worth of data. Now, there are other considerations. Was this an average month, a busy month, or a slow month? But 30 or more phenomena is a pretty doable. And remember, though, in the end, with these rules of thumb, it's to help guide our teams so that they can get through the measure phase without slipping into analysis paralysis. We want to have an understanding of what's going on in current state. We want to have both qualitative data, which is just as valuable as quant data, but with that quant data, we can use these sample size rules of thumbs to help guide our teams in terms of the effort that they put forward in the data collection plan.